In the last video, we asked questions. When we saw these definitions, we had finite, we had infinite, we had countably infinite, we had countable, and we had uncountable. And then we asked some questions. Are there infinite sets? Are there uncountable sets? Right. So we showed in the last video that there is an infinite set, that we could see the natural numbers would be an infinite set. So obviously there's a whole lot of those indeed, because the natural numbers, those have the same cardinality as all of the integers. There's plenty of infinite sets out there. But we didn't answer the question, are there uncountable sets? Are there ones that are not countably infinite or countable? So we're going to take a look at a set. Let A be a set. The power set. So if we think about the power set, so if we think about sets that we looked at, let's say, for instance, we have the empty set. How many elements are in the empty set? Well, there's 0, right? But then if we look at the power set of the empty set, this is the set containing the empty set. How many elements are in this set? Well, now there's 1. And so to visualize this, you think about the empty set being an empty box. This is an empty box. This is a box containing an empty box. So sets you can think about as boxes. So then you could talk about then this idea of the empty set being contained in a set through that idea. All right, so when we look at the power set, this does not have the same cardinality as the set itself. So any set, you look at a set with 1 element, the power set of that is going to contain 2 elements of that. So we have a different number of elements. So a corollary then is, what set would be nice to see this is true for? Well, the power set of the natural numbers does not have the same cardinality as the natural numbers. Now, in particular, the power set is going to have a larger cardinality than any set, right? If you take the set, the power set's going to have a larger or more elements in there. So if they don't have the same cardinality, that means it must be larger than countably infinite. So therefore, we do know that there are uncountable sets. This set right here, the power set of the natural numbers, whatever that looks like, that is going to be uncountable. So as a little summary at this point, what we have is, if we categorize these, some of there's overlaps and duplicates in some of these, we either have a set is going to be finite. So it has the same cardinality as 1, 2, 3, 4, 5 or something, or it's the empty set. Or it's countably infinite, but it has the same cardinality as the natural numbers, or it's finite, or same cardinality as the natural numbers, or it is uncountable. So then that means it's probably going to have a cardinality that's larger than the natural numbers. So then we have this natural question as mathematicians that we start to ask, okay, wait a minute, there's different sizes of sets now, that I do have the finite, I do have the countably infinite, now I have the uncountable. Can I get bigger than uncountable? So we have this question, are all uncountable sets the same size? Well, we know here that the natural numbers, this is going to have a cardinality that's strictly less than the cardinality of the power set of the natural numbers. But this is a set, right? And we said for any set, this is going to be true. So then that must mean that this is going to be strictly less than the power set of the natural numbers. Can I do bigger? Well, yes, that again is a set. So then this has a cardinality that's strictly less than the power set of the power set of the power set of the natural numbers. And notice I could keep going on and on and on. So how many sizes of infinity are there? Well, there's an infinite number of infinities, right? So what we said right here is that there are different sizes of infinity, right? We see that both of these are going to be infinite. Countably infinite and uncountable are both sizes of infinity. But then when we start to get to uncountable, there's an infinite number of uncountable sets. So there's an infinite number of sizes of infinity. This just keeps going on and on. And so to tie this into other things, so when we think about some other instances where we talk about things being infinite, in the Christian faith, we talk about God having infinite attributes. We talk about this God, somehow he's infinite in love, and he's infinite in justice, and he's infinite in mercy and grace and everything. Well, this says it's what size infinity, right? If we're saying it's infinite, is that just this size infinity? Is his love actually this size infinity? Is it this? Is it more? So this helps me be able to wrap my head around the idea that this idea of God being infinite in love is not just a small infinity. This could be a super gigantic infinity that we can't even begin to fathom how gigantic that would be. So some of these attributes, it leads me to worship in a different way. It leads me to think about all of these things that I thought I understood about God, or just math is just helping me blow all of that out of the water. That there's these things that how could you have different sizes of infinity? That doesn't make sense. But yet mathematically, we can show that that's true. And so we can realize that there is maybe something even deeper to appreciate about who God is. So last thing I want to mention here, notation, you might see this symbol. This is the symbol for the cardinality of the natural numbers. This is the Hebrew letter. So this is Hebrew letter Aleph. So this is the first letter of the Hebrew alphabet. So now you can joke with all your friends. You're like, yeah, not only do you see letters in algebra, then when you start taking more advanced classes, then we work with Greek letters where we have like sigmas and mu's and those things. And then now you're working with Hebrew letters. So Hebrew is what we indicate now for cardinalities for natural numbers.